Midnight Pluto, a far-off and confounding body, was once viewed as a solitary and veritable planet, a singular piece of our planetary family. Anyway, late upsetting verbalizations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have carried Pluto back into the spotlight with a surprising disclosure. They suggested that this cold world is on a potential crash course with Neptune. Yet, how could this happen, and what might be the consequences of such a gigantic event? Are we seeing an interesting eccentricity, or is there something more to this oncoming boundless episode? Go along with us as we explore the potential results of a Pluto-Neptune collision. 34 seconds. Pluto, a former planet that was consigned to a more modest status, remains a subject of interest and study in the astronomical community. According to continuous figures by leading experts, Pluto's orbit is perilously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are raising the alarm about a potentially catastrophic collision between these two celestial bodies, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's orbit around the Sun is unusual compared to any other planet in our nearby planetary system. It takes a staggering 248 years to complete a single orbit, which means that since its discovery in 1930, it hasn't even completed one round trip. However, the intrigue doesn't stop there. 1 minute and 7 seconds. Pluto's orbit is characterized by its highly eccentric shape, vastly different from the nearly circular orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination of 17 degrees to the ecliptic plane. The path Pluto follows is far more unpredictable compared to other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. Perhaps one of the most captivating aspects of Pluto's orbit is its interaction with Neptune's orbit. For at least 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, contrary to what we would expect from their positions in the planetary system. This prompts the obvious question: why hasn't Pluto crashed into Neptune? 2 minutes and 12 seconds. The answer lies in the gravitational effects of other planets. The analysis of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to explain its unusual path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood apart with its steep inclination and erratic shape. The mystery surrounding Pluto's orbit can be explained by the three-body problem in celestial mechanics. This involves understanding how three objects in space, like Pluto, Neptune, and the Sun, move and interact with each other through their gravitational forces. It's like trying to predict where they will go based on where they start and how they pull on one another. 2 minutes and 47 seconds for Pluto. This issue demonstrates how its orbit, Neptune's orbit, and the Sun's gravity all interact in a complex way. Terms like asymptotic libration, scope libration, and VZK wobbling are part of this puzzle. According to astrophysicists, what keeps all planets in their orbits is a kind of libration. In Pluto and Neptune's case, this means that whenever Pluto crosses Neptune's orbit, its position is always at least 90 degrees away from Neptune. This spatial separation is crucial for keeping their orbits from affecting each other. Degree libration, on the other hand, refers to the vertical motion of a celestial body in its orbit. For Pluto, this indicates that when it comes closest to Neptune or another giant planet, it is positioned far above their orbital plane, adding an extra layer of protection against potential collisions. 3 minutes and 50 seconds. Another critical factor in this situation is the VZK wobbling, named after three scientists, V, Z, and K, who studied how objects move in space. It describes how three space objects, like Pluto, Neptune, and the Sun, pull on one another with their gravity. This pulling affects how they move. For Pluto, the VZK wobbling helps us understand why its path near the Sun is so unusual. Despite the apparent randomness, this effect helps keep Pluto's orbit stable for an incredibly long period. The VZK wobbling shows that, although things in space might seem chaotic and unpredictable, specific patterns and forces help maintain structural control. These dynamics help safeguard Pluto's orbit, ensuring it doesn't collide with Neptune or drift off course. This three-body problem affects how we understand these orbits, particularly in how space objects pull on each other. Focusing on this helps us study Pluto, our neighboring planetary system, and distant stars and planets. 4 minutes and 23 seconds. Numerical simulations in the late 1980s revealed that, despite these predictable properties, Pluto's orbit is still wild, with small variations in initial conditions leading to significant differences over long periods. However, these unusual characteristics of Pluto's orbit have been found to maintain consistency over extremely long timescales. Later computer models have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto, where, for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. However, Neptune isn't the only factor. Jupiter's gravity also plays a significant role in protecting Pluto's orbit, and Saturn also contributes in that broad region. These tests show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a steady course for an incredibly long period, possibly even billions of years. 5 minutes and 25 seconds, perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto can continue orbiting safely in space without running into trouble. These anomalies are crucial in the broader context of the universe for maintaining the stability and consistency of celestial bodies. Without these factors, our nearby planetary system, as we know it, would be a place of far greater chaos and instability. Bodies like Pluto could indeed collide with others or be ejected from their stable orbits, triggering a cascading effect on other celestial bodies. For Pluto, especially with discussions about it potentially colliding with Neptune in the future, understanding its orbit is critical. This gives us a clearer picture of the dynamic nature of neighboring planetary systems. 6 minutes and 29 seconds. The case of Pluto shows how, even in the most seemingly unstable orbits, balance can be achieved through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of consistent observation and analysis of these phenomena to better understand our position in the universe. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a perfect example of this unpredictability. The concept of orbital resonance, which suggests the delicate dependence of a celestial body's orbit on its initial conditions, is clearly demonstrated in Pluto's case. This means that even slight changes in the dwarf planet's position or velocity can significantly alter its long-term orbit. Using virtual simulations has been crucial for research to understand how Pluto moves in space. 7 minutes and 30 seconds. These models use complex mathematics to simulate how Pluto, along with other space objects like Neptune, pulls on each other. By tweaking small details in the simulations, astronomers can see how even minor changes can have a huge impact on where Pluto ends up. In the late 1980s, these simulations revealed something very intriguing about Pluto's orbit. Despite having systems like asymptotic libration and degree libration to stabilize it, its orbit can still be astonishingly unpredictable. If you start with even a slight difference in where Pluto is or how fast it's moving, over many years, its path could end up looking completely different. 8 minutes and 3 seconds. Nevertheless, Pluto's orbit remains stable for billions of years. This suggests that Pluto's journey around the Sun has a certain order to it, even though it seems chaotic at first glance. Particularly when it involves erratic orbits like Pluto's, this presents immense challenges. The inherent nature of these systems suggests that long-term predictions are often filled with uncertainties. While numerical simulations are an essential tool for understanding and predicting the future behavior of celestial bodies, they also highlight the limitations of our calculations. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight error or deviation can dramatically change the outcomes, making precise predictions an overwhelming task. 9 minutes and 6 seconds. Moreover, the chaotic nature of large orbits like Pluto's serves as a reminder of the ever-changing and dynamic nature of the universe. While we've made tremendous strides in understanding space, Pluto's case reminds us how our knowledge of the universe is still limited. Understanding the gravitational influences of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of our nearby planetary system. It demonstrates how the presence and position of each planet can profoundly affect the stability and course of other bodies within the system. So, why are prominent astrophysicists suddenly raising concerns about a potential collision between Pluto and Neptune? Despite these complex forces attempting to prevent such an event, Neil deGrasse Tyson, a renowned astrophysicist, offers a comprehensive perspective on the mysteries of our solar system, particularly the fascinating case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, provides insightful analysis on the evolving nature of celestial mechanics and the public's fascination with the overlooked corners of space. His stance on Pluto's reclassification and the potential for further exploration of its orbit highlights the continued intrigue surrounding this distant world. 9 minutes and 35 seconds in his analysis, Tyson emphasizes how Pluto's reclassification as a dwarf planet is part of the evolving understanding of celestial bodies. He offers a book-length perspective on the mysteries of our solar system, particularly focusing on the fascinating case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, provides sharp analysis on the evolving nature of celestial mechanics and the public's interest in the overlooked corners of space. His position on Pluto's renaming underscores how science adapts and refines its definitions and categories as we learn more about the universe. His views also spark further discussions about the future of Pluto's orbit and its potential interactions with Neptune, highlighting the broader implications for our understanding of the solar system and the universe at large. As we continue to explore the cosmos and uncover the hidden complexities of celestial bodies, the example of Pluto stands as a reminder of how much we still have to learn. The delicate balance of gravitational forces and orbital mechanics continues to shape our understanding of the solar system, and the potential for new discoveries is endless. The ongoing studies and simulations surrounding Pluto's orbit are helping us refine our models, leading to a better understanding of the intricate dynamics at play. While the potential for an event such as a Pluto-Neptune collision seems distant, it serves as an important reminder of the vast and unpredictable nature of space. Understanding the forces that govern our solar system helps us not only predict future events but also appreciate the delicate balance that keeps our planet and others in their orbits.